Hello, in this lecture I will answer two questions. In the first question, we'll find out the area of this small green circle. And in the second question, we'll find out the area of this quarter circle A or B by using two different methods. So we start with the first question. In the drawing we have the right triangle ABC. Side AB equals to 6 units in its length, side BC equals to 8 units in its length, and the length of the hypotenuse AC is 10 units. Inside this triangle ABC, we have those two circles. This is the big circle that has an acceleration between this green circle and this point. This big circle touches the right triangle ABC on 3 points, 1, 2, 3, and therefore this circle is inscribed by the right triangle ABC. While this green circle touches the triangle ABC only on 2 points, and therefore it is not inscribed by triangle ABC, but it is located inside triangle ABC. Again, our task is to find out the area of this green small circle. So first of all, we find out the radius of this circle that is inscribed by the right triangle ABC. This is the right triangle ABC that could be any triangle. This circle definitely inscribed by the right triangle ABC because of the fact that it has 3 points of tendencies with this right triangle ABC, 1, 2, 3. So, therefore it is inscribed by the right triangle ABC. We know that side AB equals to A units in its length, side BC equals to B units in its length, and side AC of this right triangle ABC is equals to C units in its length. And our task, the center of this circle is at point O. And our task is to express the radius R of this circle in terms of A, B, and C, that is to say in terms of the side lengths of this right triangle ABC. So actually we'll implement rule 1 and 2 on this circle, and in this way we express the radius of R of this circle in terms of A, B, and C. This is the side length of this right triangle ABC. So we define the point of tendency of tangent AB with this circle. This point is point D. So OD is the radius of this circle. This equals to R. And the radius OD is equals to R. The radius OD is 1 to point D. This is the point of tendency of tangent AB with this circle. And whenever you have a radius that is 1 to the point of tendency, then tangent AB will be perpendicular to the radius DO. If A, according to rule 1, if AB is perpendicular to DO, it means that this angle equals to 90 degrees in its side. And this angle also equals to 90 degrees in its side according to rule 1. Likewise, we define the point of tendency of tangent BC with this circle. This point is point E. And we join points O and E together by straight line. O is of course the radius of this circle. This is equals to R. The radius OE is equals to R. The radius OE is down to point E, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is down to the point of tendency, then tangent BC will be perpendicular to the radius EO, according to rule 1. If BC is perpendicular to EO, it means that this angle equals to 90 degrees in its side. This angle also equals to 90 degrees in its side, according to rule 1. So in this quadrilateral DOEB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total must equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral DOEB, we have 4 rectangles, and therefore can relate to quadrilateral DOEB as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the rectangle DOEB, side DO must be equal to the opposite side BE. But DO is out, therefore the opposite side BE must be also equal to 1 unit in its length. Likewise, according to the same rule, in the same rectangle DEB, side OE must be equal to the opposite side DB, but OE is R, therefore the opposite side DB must be also equal to R units in its length. So in total, we found out that quadrilateral ODBE is not a rectangle but a square because of the fact that all the sides of this quadrilateral are equal to each other. So that is now quadrilateral DOBE is a square. This is the length of line segment AD. AD equals to AB minus DB. Again, AD equals to AB minus DB. So AD equals to AB, that is A, according to our definition, minus DB, that is R. So in total, AD equals to A minus R. So again on, this is line segment AD, and it is equals to A minus R units in its length. Likewise, what is the length of this line segment EC? EC equals to BC minus BE. So EC in total equals to BC, that is B, minus BE, that is R. So in total, BC equals to B minus R units in its length. The next step, we will implement rule 2 in our formula. We will implement rule 2 on this common sum point A, and we will also implement rule 2 on this common sum point C. So repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common sum point to a circle are equal. In the drawing, we have a circle. This is the common sum point P. From this common sum point P, we have two tangents to this circle, tangents PA and tangents PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. If we focus and this common sum point A, from this common sum point A, we have two tangents to this circle, tangent AD, and this is tangent, we define the touching point of the tangent AC with this circle. This point is point F. So from the common sum point A, we have two tangents to this circle, tangent AD and tangent AF, and according to rule 2, they are equal to each other. That is to say, AD equals to AF, but AD equals to A minus R, therefore AF must be also equal to A minus R units in itself, according to rule 2. Likewise, we'll focus on this common sum point C. From this common sum point C, we have two tangents to this circle, tangent CE and tangent CF. According to rule 2, they are equal to each other. That is to say, CE equals to CF. But CE equals to B minus 1, therefore CF must be also equal to B minus 1 in its name. So CF equals to B minus 1. According to our definition, AC equals to C. The opponent AC of this right triangle ABC equals to C units in its name. And C in total equals to AF plus FC. So C in total equals to AF, that is A minus R, plus FC, that is B minus R. So in total we found out that C equals to A plus B, minus R is minus 2R. Here we subtract C and add 2R to this equation simultaneously, and get that 2R equals to A plus B minus C. Here we will divide this equation by 2 and finally get that R, that is the radius of this circle that is described by data ABC, equals to A plus B minus C over 2. So this is the general formula for the radius of a circle that is described by the right triangle ABC. Because of the fact that the right triangle ABC could be any right triangle, this is a formula for a circle that is described by any right triangle. And the radius of a circle that is described by a right triangle equals to the sum of the two perpendiculars of the right triangle. That is to say, it is AB plus BC, or A plus B, minus the length of the opposite AC, that is C over 2. So the radius of any circle that is described by right triangle equals to A plus B minus C over 2. So use the new formula in order to find out the radius of this big circle that is described by the triangle ABC. We define the length of AB as A, and A equals to 6. We define the length of BC as B, and B equals to 8. And finally, we define the length of the hypotenuse AC as C, and C equals to 10. And the radius of any circle that is described by the right triangle equals to A plus B minus C over 2. Therefore, the radius of this circle that is described by the right triangle ABC equals to the radius R equals to A, that is 6, plus B, that is 8, minus C, that is 10 over 2. 6 plus 8 is 14, and 14 minus 10 is 4, and 4 over 2 is 2. So in total we should find out that the radius of this big circle that is described by the right triangle ABC equals to 2 units in its name. Or equals to 2 units in its name. We define the center of this big circle. This point is point O. We define the point of tendency of tangent AB with this circle. This point is point J. We define the point of tendency of tangent BC with this big circle. This point is point K. We define the touching point between those two circles. This point is point L. We define the point of tendency of tangent BC with this very small circle. This point is point Y. We define the point of tendency of tangent AC with this green circle. This point is point Z. And finally, we define the point of tendency of tangent AC with this big circle. This point is point M. So in the next step, we join points O and K together by a straight line. Point O is the center of this circle, point K is the point of the second step, therefore OK is the radius of this circle, this equals to 2. The radius of K that is equals to 2, the radius of K is going to point K, that is the point of tendency BC with this big circle. Whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius KO. If BC is perpendicular to KO, it means that this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to sub rule 1. Likewise, we join points O and J together by a straight line. OJ is the radius of this circle is equals to 2. And according to rule 1, those triangles are both right angles. So by doing all those constructions, we can do quadrilateral JOKB. Inside this quadrilateral JOKB, we have 1, 2, 3 rectangles. Therefore, this fourth piece here was equal to 90 degrees in size. According to the rule that said that the sum of the areas in any quadrilateral is equal to 360 degrees. So inside quadrilateral JBKO, we have 4 rectangles, and therefore can write quadrilateral JBKO is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the rectangle JOKB, side JO must be equal to the opposite side BK, but JO is 2, therefore the opposite side BK must be also equal to 2 units in its length. Likewise, according to the same rule, in the same rectangle JOKB, side JB must be equal to the opposite side OK. But OK is 2, therefore JB must be also equal to 2 units in its length. So in total, we found out that quadrilateral JBKO is a square and not a rectangle because of the fact that all of its sides are equal to each other, each side equals to 2 units in its length. Write it down. Those two circles touch each other externally at this point L. For point L is the point of tendency of those two circles with each other. We define the center of this green circle. This point is point K. And the center of the big circle is point O. We define this point O. So here we have an external arc between those two circles, that is to say those two circles touch each other externally at point 10, and therefore we can implement here rule 10. So we click on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. In the drawing, we have those two circles that touch each other externally, this point P. The center of this circle is here at point O. The center of this circle is here at point N. The straight line that connects the centers together is of course the straight line ON. And according to this rule 10, the straight line ON must pass through point P, that is the touching point. Again, the straight line ON must pass through the touching point, that is point P. Or OPM is one straight line. Again, according to this rule 10, OPM is one straight line. Therefore, OM equals to OP plus PM. We can implement rule 10 in our drawing. In our drawing, we will equilibrate between those two circles at point L. The center of this big circle is here at point O. The center of this small green circle is here at point K. The straight line that connects the circles together is of course the straight line OK. And according to rule 10, the straight line OK must pass through point L, that is their touching point. Or the straight line OK must pass through their touching point, that is point L. So if you join points O and K together by straight line, the straight line OK must pass from point L, that is their touching point, according to rule 10. So we join points O and K together by straight line. It is very easy to say from the drawing that the straight line OK passes through point L, that is the touching point, exactly according to rule 10. And according to rule 10, because of the fact that OLK is one straight line, it means that OK equals to OL plus LK. So OK equals to OL. OL is the radius of this circle, this is 2. Plus LK. LK is the radius of this green circle. We define the radius of this green circle as x, so therefore LK equals to x. So according to rule 10, OK equals to OL plus LK. So OK in total equals to OL, that is 2, plus LK, that is x. So in total we should found out that OL equals to 2 plus x units in its length. So it is known. OK equals to x plus 2 units in its length. In the next step, we'll join points K and Y together by straight line. KY is of course the radius of this green small circle, that is equals to x. And according to rule 1, those two angles are both right angles. Likewise, we'll join points K and Z together by straight line. Okay, again, we'll join points K and Z together by straight line. KZ is of course the radius of this circle, that is equals to x. And those two angles are both right angles according to rule 1. In the next step, we will join points C and K together by a straight line. By joining point C and K, we can derive those two right angles. Okay, again. By joining point C and K, we created those two right angles. So in the next step, we will prove that those two right angles can point to each other according to side rule. So we have to prove that this is the right angle ZKC, the upper right angle. And it can point to this lower right angle KYC. And again, we have to prove that the right upper triangle ZKC can point to the right lower triangle, triangle KYC. So why those two right triangles can point to each other? First of all, if you focus on the common center point C, for the common center point C, we have two tangents to this green circle. Tangent CZ and tangent CY. And according to rule 2, they are equal to each other. That is to say, CZ equals to CY. So CZ equals to CY according to rule 2. It is down here that CZ equals to CY. So why those two triangles can go into each other? First of all, CZ equals to CY according to rule 2. KZ equals to KY equals to X. They are both the radii of the green circle. They equals to X, and therefore they are equal to each other. So I write it down. KZ equals to KY equals to 2. KZ equals to KY equals to 2. They are both the radii of the circle. Therefore they are equal to each other. And finally, KC is a common side that belongs to both triangles, so I can write down that KC equals to itself as a common side that belongs to both triangles. And again, KC equals to itself as a common side that belongs to both triangles. So we actually proved that all the three sides of this upper right triangle KZC are correspondingly equal to all the three sides of this lower right triangle KYC. Therefore, those two right triangles can go into each other according to side rule. So I write it down. I can prove that the upper right triangle KZC congruent, this is the sign of congruent, to the lower right triangle KYC. According to side rule. And from the fact that those two right triangles can go into each other, we will derive that their corresponding angles, those two corresponding angles must be also equal to each other in their sizes, according to the rule that said that corresponding angles can go into triangles are equal to each other. That is to say, those two right triangles can go into each other, therefore their corresponding angles must be also equal to each other in their sizes. So if you found out that angle ZCK equals to this angle KCY. And again, found out that angle ZCK of the upper right triangle ZKC equals to angle KCY of the lower right triangle KYC. So if you define one angle as alpha, then the other angle must also equal to alpha because they are equal to each other according to the rule that I mentioned. So after we found out that KC, the common side KC, is the angle bisector of angle ACB. Which we found out again, the common side KC is the angle bisector of angle ACB. Why? Because of the fact that KC bisects angle ACB in two halves. Each half equals to alpha. So write it down. KC is angle bisector. AB is abbreviation for angle bisector of angle ACB. Angle ACB is bisected into two halves by angle bisector KC. Each half equals to alpha. So KC is angle bisector of angle ACB. In the next step, we'll join points O and M together by straight line. OM is of course the radius of this big circle, is equals to 2, according to what we already found out. And those two angles, each of them is equal to 90 degrees in size according to rule 1. So in the next step, we will prove that those two right big triangles can go into each other according to side rule. That is to say, we will prove that the upper right big triangle OMC can go into this right lower triangle OKC. So why those two triangles can go into each other? First of all, we will focus on this common side point C. From this common side point C, we have two tangents to the big circle, tangent CM and tangent CK. And according to rule 2, they are equal to each other. That is to say, CM equals to CK. So in total, we found out that CM equals to CK according to rule 2. Or side CM. So we have to prove that the right triangle OMC can went to this right triangle OKC. So first of all, we found out that side CM of the right triangle OMC equals to side CK of the right triangle OKC, according to rule 2. In addition, those two sides are both the area of the big circle, that equals to 2, and therefore they are equal to each other. So we found out that side OM of the right triangle OMC is equal to side OK of the right triangle OKC. And again, side OM of the right triangle OMC is equal to side OK of the right triangle OKC. The above the radar of the circle is equal to 2, and therefore they are equal to each other. And finally, OC, actually, we join points O and C together by a straight line, and therefore OC, of course, is a straight line by our construction. Okay, we join points O and C by the straight line, and therefore OC is a straight line. So OC, the straight line OC equals to itself, and therefore there's a common side that belongs to both big right triangles. So you know, side OC is a common side that belongs to both triangles, so we can write down that OC equals to itself is a common side that belongs to both big right triangles. So to that, we found out that all the three sides of this big right triangle OMC correspond equal to all the three sides of this lower right triangle OKC. And therefore, those two big right triangles can point to each other according to side rule. So it is on if you found out that the big right triangle OMC can point, this is the sign of can point, to the right lower triangle OKC according to side rule. And from the fact that those two big right triangles can point to each other, we will derive that their corresponding angles must be also equal to each other in their sizes. Those are the two corresponding angles of those two right triangles. And their corresponding angles must be equal to each other in their sizes, according to the rule that corresponding angles in right triangles are equal to each other. Those two big right triangles can point to each other, and therefore their corresponding sides must be also, their corresponding angles must be also equal to each other in their sizes. So angle MCO or the right triangle MCO equals to angle OCK or the right triangle OCK. So if you find one angle itself and the other angle must also equal to alpha because they are equal to each other according to the rule that I mentioned. So in total we found out that OC is also angle bisector of angle ACB. Why? Because of the fact that OC bisects angle ACB into two halves, each half equals to alpha. So let it know. And we found out that OC is also angle bisector. AB is a version for angle bisector of angle ACB. OC bisect the big angle ACB into two halves, each half equals to alpha. But we only found out that KC is also angle bisector of the big angle ACB. KC is also angle bisector of the big angle ACB. But we know that angle ACB is only one angle bisector. The big angle ACB is only one angle bisector. So, and you know, the big angle ACB is only one angle bisector. And for that reason, if OC is angle bisector of angle ACB and KC is also angle bisector of angle ACB, it means that all the 3 points O, K, and C must be located on one straight line. So it is not. Therefore, points O, K, and C must be located on the same straight line. Here SL is abbreviation for straight line. In the straight line, what is the straight line that all the 3 points O, K, and C are located on? Is the angle bisector of angle ACB. This is the angle bisector of angle ACB. So those 3 points O, K, and C are located on the same straight line. That is The straight line is the angle bisector of angle ACB. Or in other words, we actually found out that OC passes through point K. Okay, OC passes through point K. So as you know, OC passes through point K. Because of the fact that OCK are located on the same straight line. What is the length of this line segment KC? From the drawing, it is very easy to see that KC in total equals to BC minus BK. Again, BC minus BK equals to KC. So it is not if we found out that the missing line segment KC is equal to BC minus BK. Repeat again. The missing line segment KC equals to BC minus BK. So KC equals to BC is 8 according to what is given as a question. Minus BK. BK is 2. This is the radius of the circle, this is 2. It's not the radius, but it equals to 2. So in total, KC equals to 8 minus 2, that is 6. KC equals to 6 units in its length. In the next step, we will implement the Pythagoras theorem on this right lower triangle OKC. This right lower triangle OKC, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle OKC, here by PT is the abbreviation for Pythagoras theorem. So in this right triangle OKC, OC squared, that is the square of the hypotenuse, equals to OK squared plus KC squared. So the norm OC squared, that is the square of the hypotenuse, equals to OK squared plus KC squared. And again, in the right triangle OKC, according to the Pythagoras theorem, OC squared, that is the square of the hypotenuse, equals to OK squared plus KC squared. OC is the missing side, so we leave it as it is, so it is OC squared equals to OK squared. OK is 2, therefore OK squared is 2 squared, that is 4, plus KC squared. We just right now found out that KC equals to 6, so KC squared equals to 6 squared, that is 36. So total we found out that OC squared equals to 4 plus 36, that is 40. OC squared equals to 40. Here we take out all those equations. And finally we get that OC equals to the square root of 40. Here we substitute 40 by 4 times 10. The square root of 4 is 2, so we'll take 4 out of the roots. Again, the square root of 4 is 2. Besides the root, we left only with 10. So in total, we found out that the length of the missing hypotenuse OC is equals to 2 times square root of 10 units in its length. So actually, this is the missing hypotenuse OC. that is equal to 2 times square root of 10 units in its length. What is the length of this line segment KC? From the drawing, it is very easy to see that KC in total equals to OC minus OK. And again, KC equals to OC minus OK. OC minus OK. So, I can now, the missing line segment KC is equal to OC minus OK. And again, the missing line segment KC equals to OC minus OK. So KC equals to OC. OC just write down formula that I found OC equals to 2 times square root of 10. Minus OK. According to rule 10, OK equals to x plus 2. Yeah, OK equals to x plus 2. So KC in total equals to 2 times square root of 10. We'll open the brackets here. After we open the brackets, this expression will be equal to minus x minus 2. So in total, we found out that the missing line segment KC equals to 2 times square root of 10 minus x minus 2. This is the missing line segment KC. That equals to 2 times square root of 10 minus x minus 2. This is the right angle OKC. In this right angle OKC, this angle is alpha. This is the right angle, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it equals to 180 degrees. That is the sum of degrees in any triangle. Likewise, in this right small triangle KYC, this is angle alpha, this is the right angle, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of angles in any triangle is equal to 180 degrees. So this missing angle C and KY equals to 90 degrees minus alpha in its size. In the next step, we'll prove that the big right angle OKC is similar to this small right angle KYC according to angle similarity rule. So why those two right angles are similar to each other? First of all, this is angle alpha, that is the common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as the common angle that belongs to both triangles. In addition, those two angles are both right angles and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So in total, we found out that all the figures of the right angle OKC are corresponding equal to all the figures of this right angle KYC. Therefore, those two right angles are similar to each other according to angle similarity rule. So I think now we found out that this is the right big triangle OKC. Right big triangle OKC is similar. This is the sign of similar to this small right triangle KYC according to angle similarity rule. And for the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We derive that side OK of the big right triangle OKC outside KY of the small right triangle KYC is equal to the hypotenuse OC of the big right triangle OKC over KC. Repeat again. From the fact that those two right triangles are similar to each other, we derive that the following relationship exists between the sides. We derive that side OK of the big right triangle OKC over side KY of the small triangle KYC is equal to side OC of the big right triangle OKC or side KC of the right lower triangle, right lower small triangle KYC. OK is 2. Over KY. KY is X. It is the radius of the grand circle. And it's equals to OC. OC is the hypotenuse of the big right triangle OKC. It is equals to 2 times root of 10 units in its length. Over KC. We already found out that KC equals to 2 times root of 10 minus X minus 2. So to that, we found out that 2 over X equals to 2 times root of 10 over 2 times root of 10 minus X minus 2. Here we have 2 on both sides of this equation, so 2 will get cancelled. So the next step, we'll cross multiply this equation. And we get that 2 times root of 10 minus X minus 2 equals to X times root of 10. Here we will add X to this equation. And we get that 2 times root of 10 minus 2 equals to X times root of 10 minus X. Here we take two as a common factor from those two expressions. So inside the brackets we get square root of 10 minus 1. And it equals to this expression. So here we take X as a common factor from those two expressions. So in the brackets we left only with square root of 10 minus 1. So in total, if we found out that 2 times square root of 10 minus 1 equals to X times square root of 10 minus 1. Actually, we added X to this equation. So here it is plus X. Because we added X to both sides of the equation. So here it is plus X. So here also we have, so it is square root of 10 plus 1 because it is positive. So here we have in total 2 times square root of 10 minus 1 equals to X times square root of 10 plus 1. So here we will divide this equation by square root of 10 plus 1, and finally you get that X, that is the radius of this green small circle, is equal to square root of 10 minus 1 over square root of 10 plus 1. So here we will multiply both the numerator and the denominator of this expression by square root of 10 minus 1. This is allowable to multiply this both sides of the equation by square root of 10 minus 1, because of the fact that square root of 10 minus 1 over square root of 10 minus 1 is 1, so and it is allowable to multiply anything by 1. So x equals to the square root of 10 minus 1, and we multiply it by square root of 10 minus 1 over square root of 10 plus 1, and multiply square root of 10 by 1, multiply square root of 10 plus 1 by square root of 10 minus 1. So in total, if you found out that x equals to the square root of 10 minus 1 times the square root of 10 minus 1 over square root of 10 plus 1 times square root of 10 minus 1. So x equals to square root of 10 minus 1 times square root of 10 minus 1 is square root of 10 minus 1 square over square root of 10 plus 1 times square root of 10 minus 1. We use the algebraic identity that said that a plus b times a minus b equals to a square minus b square. So according to this algebraic identity, we get that square root of 10 plus 1 times square root of 10 minus 1 equals to the square root of 10 squared, that is 10, minus 1 squared, that is minus 1. So in total, this expression equals to 10 minus 1, that is 9. So here we have x equals to the square root of 10 minus 1 square over 10 minus 1 is 9. So in total, if you found out that x, that is the radius of the green circle, this is the radius of this green circle, x equals to the square root of 10 minus 1 square over 9. So again, in total, found out that x, the radius of the green small circle, is equal to the square root of 10 minus 1 square over 9. Our task is to find out the area of this green circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of this green circle must be equal to pi times the radius of this green circle squared. That is, the radius of this green circle is x, therefore it is pi times x squared. So it is pi times x squared. X is square root of 10 minus 1 here actually so the radius of the green circle equals to pi times x squared. This is actually pi times square root of 10 minus 1 squared I made the mistake. See, the radius of the green circle x, it is equals to, here we have here we have 2 times square root of 10 minus 1 equals to x times square root of 10 plus 1. So here I forgot the 2. Actually divided this equation by square root of 10 plus 1. So here we will get that x equals to 2 over times square root of 10 minus 1 over square root of 10 plus 1. So here we have 2, I forgot the 2. Here also we have 2. Here also we have 2. So in total, I just forgot the 2 here. So in total, here we have 2. We have 22. So pi x squared is pi times x squared. X is 2 ninths times square root of 10 minus 1 squared. Just forgot the 2. So here we have to square 2 ninths and also square root of 10 minus 1 squared. 2 ninths squared is 2 squared, that is 4, over 9 squared, that is 81. We have also pi, and it equals to square root of 10 minus 1 squared. So to the follow the area of the green small circle, that is the area that we're looking for in this question, equals to 4 pi over 81 times square root of 10 minus 1 squared. Square root of 10 minus 1 squared equals to the square root of 10 squared, that is 10, plus 1 squared, that is 1, plus 2 times square root of 10 times 1. So total this expression equals to 4 pi over 81, 10 plus 1 is 11, plus 2 times square root of 10 squared. Okay, it is squared. Here we have squared. So it is 4 pi over 81, and we have 11 minus 2 times square root of 10 squared. That's actually 11 squared, that is 121, plus 2 times square root of 10 squared is 2 squared, that is 4, times square root of 10 squared is 10, so 4 times 10 is 40. Minus 2 times 11 is minus 22, minus 22 times 2 is minus 44 times square root of 10. So it is minus 44 times square root of 10. Here we have 121 plus 40 is 161. Minus 44 times square root of 10. This expression in total equals to 274.7 square roots in size. So if you found out that the area of the green small circle, that is the area that we are looking for in this question, this equals to 274.7 square roots in size. So we finish with the first question. The next step I present you the second question, and we solve the second question by using 2 different methods. In the second question, our task is to find out the area of this quarter circle AOB. So in the drawing, we have quarter circle AOB. We know that line segment OQ equals to line segment PQ in its length. This is angle PQB, this is a right angle, and QB equals to 1 unit in its length. This is a right angle, it is so in any quarter circle. Repeat again, our task is to find out the area of this quarter circle AOB. AO equals to OB, the above the radii of the quarter circle, so we will find the radius of this quarter circle is x. So AO, the radius of AO equals to x, according to our definition. OB also equals to x units because it is also the radius of this quarter circle AOB. Therefore it equals to x. In total, OQ equals to OB minus QB. So it is now OQ equals to OB minus QB. So in total, OQ equals to OB is x, minus QB is 1. So in total, we found out that OQ equals to x minus 1 units in its length. But according to what is given as the equation, OQ equals to QP. OQ is x minus 1, therefore QP must be also equal to x minus 1 units in its length, because they are equal to each other, according to what is given as the question. In the next step, we will complete this quarter circle to a circle. We completed the quarter circle to a circle, and we'll extend the radius BO by straight line until it touches the circle. And we will define the touching point of the radius of the extended radius BO with this circle. This point is point N. Likewise, we'll extend line segment PQ until it touches the circle. And we'll define the touching point of the extended line segment PQ with this circle. This point is point M. PQ, actually QM is the mirror image of PQ. Again, QM is the mirror image of PQ. Here, NB is the axis of symmetry. That is to say, the circle is divided into two semicircles, and the axis of symmetry is NB. So if we flip this upper semicircle towards us, point P and point M will merge with each other. And again, if we flip this upper semicircle towards us, point P and point M will melt with each other. And because of the fact that PQ, QM is the mirror image of PQ, it means that PQ equals to QM in its length. This is like if you look in the mirror, you see yourself exactly as the same size as you in reality, but in the opposite direction. Therefore, QP, because of the fact that QM is the mirror image of PQ, means that QM equals to PQ in its length. But PQ is x minus 1, therefore QM must be also equal to x minus 1 units in its length. So, in the next step, ON is of course the radius of this circle is equals to x. In the next step, we will implement rule 65 in our drawing in our circle. So repeat quickly rule 65. Rule 65 is true in any circle. In any circle, if chord AB intersects with chord CD at point O, then the following equation is true. Again, chord AB intersects with chord CD at point O. So whenever two chords are intersect with each other inside the circle, the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. You can definitely implement rule 65 in our drawing. Now drawing, this is chord NB that intersects with chord PM at point Q. Again, chord NB intersects with chord PM at point Q. So all the requirements for rule 65 are satisfied, and therefore we can implement here rule 65. So write it down. Chord NB intersects with chord PM at point Q. Repeat again. The intersection point of chord NB with chord PM occurs at point Q. Chord NB intersects with chord PM at point Q. Therefore, according to rule 65, the following equation is true. NQ times QB equals to PQ times QM. Again, NQ times QB equals to PQ times QM. According to rule 65, NQ times QB equals to PQ times QM. NQ equals to x plus x minus 1, that is 2x minus 1 times QB. QB equals to 1, and is equals to PQ. PQ is x minus 1 times QM. QM is also x minus 1. So in total, we found out that two x minus 1 times 1 equals to x minus 1 times x minus 1. So it is 2x minus 1 equals to x minus 1 squared. 2x minus 1 equals to x minus 1 squared. X minus 1 squared equals to x squared. Plus 1 squared, that is 1, minus 2 times x times 1, that is minus 2x. Here we add 1 to this equation, and we get that 2x equals to x squared. 1 plus 1 is 2, minus 2x. Here we subtract 2x from this equation, and finally we get that 2x minus 2x is 0, equals to x squared plus 2 minus 2x minus 2x is minus 4x. So in total we actually found out that x squared minus 4x plus 2 equals to 0. And again, found out actually that x squared minus 4x plus 2 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. The general formula for a quadratic equation: a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. So x equals to another specific quadratic equation, that is to say x squared minus 4x plus 2 equals to 0. The variable that we are looking for is x, and x is the radius of this quarter circle. X is the radius of the quarter circle, the coefficient a in our specific quadratic equation is 1. The coefficient b is minus 4. And the coefficient c is 2. So actually have all the data that is needed in order to find out the value of x, that is the radius of the quarter circle. So we just have to put the data for this specific quadratic equation in this general formula for x, and this way we find out the value of the values of x, because x must have two solutions. So we'll do it now, and we'll get that x equals to minus b. b is minus 4, therefore minus b is minus 4, that is plus 4, plus minus square root of b squared. b is minus 4, therefore b squared is minus 4 squared, that is 16. Minus 4 times a is 1, so minus 4 times 1 is minus 4 times c. Minus 4 times c, that is 2, is minus 4 times 2, that is minus 8 over 2a. a is 1, so 2a is 2 times 1, that is 2. So in total we found out that x equals to 4 plus minus, inside the root we have 16 minus 8 is 8 over 2. So x equals to 4 plus minus, we substitute 8 by 4 times 2. Over 2. So x in total equals to 4 plus minus, the square root of 4 is 2, so we'll take 4 out of the root, so inside the root we'll have only with 2. Again, the square root of 4 is 2, inside the root we'll have with 2 over 2. So in total we actually found out that x equals to 4 over 2 is 2, plus minus 2 over 2 is 1. So in total, this expression equals to square root of 2. So in total, we found out that x equals to 2 plus minus square root of 2. So here we have two solutions that are possible for x. X is the radius of the quarter circle. The first solution for x is that x is equals to 2 minus square root of 2. 2 minus square root of 2 is equals to 0.59. And again, according to the first solution, x, that is the radius of the quarter circle, is equals to 0.59 units in its length. OQ equals to x minus 1. OQ, line segment OQ equals to x minus 1 units in its length. OQ is a length, and as a length it must be a positive number. But OQ equals to x minus 1. It means that x minus 1 must be a positive number. What is a positive number? It is a number that is greater than 0. So therefore x minus 1 must be greater than 0. Here we add 1 to this inequality, and get that x must be greater than 1. If x must be greater than 1, x can never be equal to 0.59, that is less than 1. Therefore, the first solution for x is incorrect solution. So we cancel this solution for x and we'll take into account only the second solution for x. The second solution for x is as follows. X equals to 2 plus square root of 2. So the radius x of the quarter circle equals to x plus square root of 2 units in its length. Our task is to find out the area of this quarter circle A or B. The area of any quarter circle is equal to the area of the circle over 4. The area of this circle is pi x squared because the radius is x. And therefore the area of the quarter circle must be equal to pi x squared over 4. So it is pi over 4 times x squared. X is 2 plus square root of 2. Therefore x squared is 2 plus square root of 2 squared. So in total we found out that the area of the quarter circle, the area of this quarter circle, that is the area that we are looking for this question, is equals to pi over 4 times 2 plus square root of 2 squared. This actually equals to, this expression in total equals to 9.155 square units in size. So again, we found out that the area of the quarter circle, that is the area that we are looking for this question, is equal to 9.155 square units in size. The area of this quarter circle A or B equals to 9.155 square units in size. So we finish with the first method. In the next step I present to you how to find out the area of this quarter circle A or B according to the second method. In the second method, we define the radius of this quarter circle as x. AO equals to OB, the above the area of the quarter circle, is equals to x according to our definition. AO equals to x, the radius AO equals to x, and the radius OB also equals to x. OQ equals to OB, this is x, minus QB, this is 1. So in total, OQ equals to x minus 1, it's in its length. But PQ equals to OQ, and OQ equals to x minus 1, therefore PQ must also equal to x minus 1, it's in its length. OB is the radius of this quarter circle, therefore it is absolutely a straight line. So if you focus on the upper side of the straight line OB at point Q, here the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the areas on one side of the straight line is equal to 180 degrees. So which areas we have at the upper side of the straight line OB at point Q? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we'll join points O and P together by straight line. Point O is the center of the quarter circle, point P is the point on the quarter circle itself, so therefore OP is the radius of this quarter circle. This equals to x according to our definition. In the next step, we will implement the Pythagoras theorem on this right rectangle, triangle POQ. In this green right triangle POQ, according to the Pythagoras theorem, PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. So I write it down. According to the Pythagoras theorem, in this green right triangle POQ, PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. And again, in this right triangle POQ, according to the Pythagoras theorem, PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. PO equals to x, therefore PO squared is x squared, and it equals to PQ squared. PQ is x minus 1, therefore PQ squared is x minus 1 squared, plus OQ squared. OQ is also x minus 1, therefore OQ squared is x minus 1 squared. So in total, we actually found out that x squared equals to x minus 1 squared plus x minus 1 squared. So x squared equals to 2 times x minus 1 squared. X squared equals to 2. Here we'll open the brackets of this expression. X minus 1 squared equals to x squared plus 1 squared, that is 1, minus 2 times x times 1, that is minus 2x. So then we actually found out that x squared equals to 2 times x squared plus 1 minus 2x. So x squared equals to 2 times x squared, 2 times 1 is 2 plus 2, and 2 times minus 2x is minus 4x. Here we subtract x squared from this equation, and get that here we left with 0 equals to 2x squared minus x squared is x squared minus 4x plus 2. So in total we found out that x squared minus 4x plus 2 equals to 0. We already found out that the solution of this quadratic equation, according to the first method, x equals to the square root of 2 plus 2. And our task is to find out the area of this quarter circle A or B. The area of quarter circle A or B equal to pi x squared over 4. So it is pi over 4 times x squared. X is square root of 2 plus 2. And therefore x squared is square root of 2 plus 2 squared. And this expression in total pi over 4 times square root of 2 plus 2 squared is equal to 9.155 square units in its size. So here, on both methods, we found out that the area of this quarter circle, that is the area of this quarter circle A or B, that is the area that we're looking for in this question, is equal to 9.155 square units in size. So we finish with the second question. In the next step, I will summarize the lecture. We start with the repetition of the first solution of the first question, and then repeat on the solution of this second question on both methods. In the first question, our task is to find out the area of this small circle. So, in the drawing, we have the right angle ABC. This is the right angle. Side AB equals to 6 units in its length. Side BC of this right angle ABC equals to 8 units in its length. And the length of the hypotenuse AC is 10 units in its length. In addition, inside this right angle ABC, we have those two circles that touch each other exactly at this point. This is the big circle that is definitely inscribed by that right angle ABC because of the fact that it has 3 points of tendency with this right angle ABC. 1, 2, 3. Whereas this small circle is not inscribed by triangle ABC because it has only 2 points of tendencies with this triangle ABC. So in the first step, we actually found out a formula that will help us to find out the radius of the circle that is described by the right angle. So actually, this is the right angle ABC that could be any right angle. Inside this right angle ABC, we have this circle that is described by the right angle ABC. Side AB equals to 1 unit in its length. Side BC equals to 1 unit in its length. The hypotenuse AC equals to 3 units in its length. And our task is to find out the radius of this circle that is described by this right angle ABC. That is to say, we have to express the radius R of this circle in terms of A, B, and C. In terms of the side lengths of this triangle ABC, that is to say A, B, and C. So, Repeat again. This is the right angle ABC that could be any right angle. Inside this right angle ABC, we have this circle that is described by this right angle ABC. And our task is to find out the radius of this circle that is described by the triangle ABC in terms of A, B, and C. We have to express the radius R in terms of A, B, and C, that is the sine radius of this triangle ABC. So we implemented rule 1 and 2 on this drawing in order to find out the radius of this circle in terms of A, B, and C. Point O is the center of this circle. Point on the circle is therefore OD is the radius of the circle is equals to R. The radius OD is equals to R. The radius OD is drawn to point D. This is the point of tendency of tangent AB with this circle. Whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius DO. If AB is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and E together by side line. E is the point of tendency of tangent BC with this circle. OE is of course the radius of this circle, this is equals to R. Again, according to rule 1, those two angles are both right angles. So in quadrilateral DOEB, we have 1, 2, 3 angles. Therefore, this fourth angle must be equal to 90 degrees in size. According to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral ODBE, we have 4 angles, and therefore can relate to quadrilateral ODBE is a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle ODBE, side OD must be equal to the opposite side BE, but OD is out, therefore the opposite side BE must be also equal to 1 units in its length. Likewise, according to the sum rule, in the sum rectangle ODBE, side OE must be equal to the opposite side DB. But OE is out, therefore the opposite side DB must also equal to 1 unit, must be also equal to 1 unit in its length. So in total, we found out that quadrilateral ODBE is not a rectangle but a square because of the fact that all of its sides are equal to each other, its side equals to R. What is the length of this line segment EC? EC equals to BC, that is B, minus BE, that is R. So in total, EC equals to B minus R. Likewise, what is the length of line segment AD? AD in total equals to AB, that is A, minus BD, that is R. So in total, AD equals to A minus R units in its length. In the next step, we focus on this common sum point A. From this common sum point A, we have two tangents to this circle, tangent AD and tangent AD and tangent AF. And according to rule 2, they are equal to each other. That is to say, AD equals to AF, but AD equals to A minus R, therefore AF must be also equal to A minus R units in its length. Likewise, we focus on this common example point C. From this common example point C, we have two tangents to this circle, tangent CF and tangent CE. And according to rule 2, they are equal to each other. That is to say, CF equals to CE equals to CF. But CE is B minus R, therefore CF must be also equal to B minus R units in its length. So in total, we found out that the opponent AC, that equals to C according to our definition, equals to AF plus FB. AF plus FC. C equals to AF plus FC. So C equals to AF, that is A minus R, plus FC, that is B minus R. So in total, C equals to A minus R plus B minus R. So C equals to A plus B minus R minus R is minus 2R. So in total, C equals to A plus B minus 2R. Here, we subtracted C and added 2R simultaneously to this equation, and we found out that 2R equals to A plus B minus C. Here we divided this equation by 2, and we found out that the radius of this circle that is described by that triangle ABC, that would be any right triangle, equals to A plus B minus C over 2. A plus B is the sum of the two perpendiculars of the right triangle that blocks the circle, minus the length of the hypotenuse C over 2. So it is true for any circle, for a circle that is described by any right triangle. This equation. R equals to A plus B minus C over 2. So we implemented this new formula in order to find out the radius of this circle that is described by the right triangle ABC. We define the length of AB as A is equals to 6. We define the length of side BC of this right triangle ABC as B, and B equals to 8. And finally, we define the length of the hypotenuse AC as C, and C equals to 10. And the question for the radius of this circle is as follows: R equals to A plus B minus 0 to A is 6, B is 8, and C is 10. So in total, the radius of this circle R equals to 6 plus 8, that is 14, minus 10 over 2. 14 minus 10 is 4, and 4 over 2 is 2. Total, we found out that the radius of this big circle that is described by the right triangle ABC is equals to 2 units in its length. R equals to 2. Those two circles have an acceleration between them at point L. That is to say, they touch each other accelerate at point L. The center of this circle is at point O, the center of this circle is at point K. So here we can implement rule 10 in our drawing. So repeat quickly rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the centers together passes through their touching points. In the drawing, we have those two circles that touch each other externally at this point P. The center of this circle is here at point O. The center of this circle is here at point M. The straight line that connects the centers, together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through their touching point at this point P. Or the straight line OM must pass through point P, that is their touching point. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. And therefore, OM in total equals to OP plus PM. So we can implement rule 10 in our drawing. When put in our drawing, we have an acceleration between those two circles at point L. The center of this circle is here at point O. The center of this green circle is here at point K. The straight line that connects the centers together is OK. And according to rule 10, the straight line OK must pass from point L, that is the touching point. So if we join points O and K together, it must pass from point L according to rule 10. Indeed, we join points O and K together by straight line, and it is very easy to see that OK definitely passes from point L, that is the touching point, exactly according to rule 10. And therefore, OK in total equals to OL plus LK. So OK in total equals to OL, that is 2, it is the radius of this big circle, plus LK, this is X. X is the radius of this green semicircle, it's green circle. So in total, OK equals to X plus 2. OK equals to X plus 2. So in the next step, we join points K and Y together by straight line. KY is the radius of this green small circle equals to X, and according to rule 1, those two angles are both right angles. Likewise, we join points X and Z together by straight line. XZ is the radius of this green small circle, this is X, and according to rule 1, those two angles are both right angles. And in the next step, we join points C and K together by straight line. By joining points C and K, we created those two right triangles. So, and if you focus on the common side point C, from the common side point C, we have two tangents to the green circle, tangent CZ and tangent CY. And according to rule 2, they are equal to each other. That is to say, CZ equals to CY. So in the next step, we prove that those two right triangles can run to each other according to side rule. So we can prove that the upper right triangle ZKC can run to the lower right triangle KYC. So why those two right triangles can run to each other? First of all, we just right now found that CZ equals to CY. In addition, those two sides are both the other of the green circle. This equals to X, and therefore they are equal to each other. And finally, KC is the common side that belongs to both triangles, so we can write down that KC equals to itself as the common side that belongs to both triangles. So in total, we should find out that all the three sides of this right triangle ZKC are corresponding equal to all the three sides of this right triangle KYC, and therefore those two right triangles can point to each other according to side rule. Okay, again, we should hold on in total that the right triangle KZC can point, this is the sign of can point to the right lower triangle KYC according to side rule. And from the fact that those two right triangles can point to each other, we know that those two corresponding angles must be equal to each other and their sizes. According to the rule that corresponding angles can point triangles are equal to each other, those two right triangles can point to each other, and therefore those two corresponding angles must be also equal to each other and their sizes. So if we find the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. So in total, we found out that KC is the angle bisector of angle ACB. Why? Because of the fact that KC bisects angle ACB into two halves. It's half equals to alpha. Okay, again, total, we found out that KC, the common side KC, is the angle bisector. AB is the abbreviation for angle bisector. KC is the angle bisector of angle ACB. So in the next step, we join points O and M together by side line. Side line OM is the radius of this angle, equals to 2, and those two angles are both right angles according to rule 1. So in the next step, we prove that those two big right angles can point to each other according to side rule. That is to say, we prove that the right upper triangle AMOC can point to this right lower triangle OKC according to side rule. So all those two right triangles can point to each other. So if you focus on this common sum point C, from this common sum point C, we have two tangents to the big circle, tangent CM, and tangent CK. And according to all two, they are equal to each other. That is to say, CM equals to CK. So CM equals to CK according to rule 2. Likewise, those two line segments are both the order of the big circle, that equals to 2, and therefore they are equal to each other. And finally, CO, we join point C and O by side line, and therefore CO is the side line according to our construction. So CO equals to itself is the common side that belongs to both triangles. So we can write down that CO equals to itself is the common side that belongs to both triangles. So in total, we found out that all the three sides of this big right triangle OMC are corresponding equal to all the three sides of this right lower triangle OKC. And therefore, those two right triangles can point to each other according to side rule. So again, we found out in total that the right upper triangle OMC can point, this is the sign can point to the right lower triangle OKC according to side rule. And from the fact that those two right big triangles can point to each other, we will derive that those two corresponding angles must also equal to each other in their sizes. According to the rule that I already mentioned, corresponding angles can point triangles are equal to each other. Those two right big triangles can point to each other, and therefore these corresponding sides must also equal to each other in their sizes. So if we find the size of this angle is alpha, then the size of this angle must also equal to alpha, because they are equal to each other according to the rule that I mentioned. So in total, we found out that OC is angle bisector of angle ACB. Why? Because of the fact that OC bisects angle ACB into two halves, each half equals to alpha. So if again, we found out that OC is angle bisector, if AB is the portion for angle bisector, so OC is angle bisector of angle ACB. But we already found out that KC is also angle bisector of angle ACB. And OC is angle bisector of angle ACB, and KC is also angle bisector of the same angle ACB. But we know that angle ACB is only one angle bisector. Angle ACB is only one angle bisector. And therefore, because of the fact that angle ACB is only one angle bisector, and OC is angle bisector, and KC is also angle bisector, it means that those 3 points O, K, and C must be located on the same straight line. And again, we derive that from the fact that OC is only one angle bisector, that the 3 points O, K, and C are located on the same straight line. And the straight line is, of course, the angle bisector of angle ACB. The straight line is the angle bisector of angle ACB. So those 3 points O, K, and C are all located on the same straight line that is the angle bisector of angle ACB. Or we can say that OC passes through point K. Because of the fact that all KC are located on the same straight line, it means that OC passes through point K. OC passes through point K. What is the proof? KC in total equals to BC, that is 8, minus BK, that is 2. In total, KC equals to 8 minus 2, that is 6. This times KC equals to 6 units in itself. But again, KC equals to BC minus BK. BC is 8, BK is 2, so in total BK is 2, so in total KC equals to 8 minus 2, that is 6. KC equals to 6 units in itself. In the next step, implement the Pythagoras theorem on this right angle OKC. According to the Pythagoras theorem, in a right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right angle, again OKC, OC squared, that is the square of the hypotenuse, equals to OK squared plus KC squared. And again, this right lower angle OKC, according to the Pythagoras theorem, OC squared, that is the square of the hypotenuse, equals to OK squared plus KC squared. OC is the missing side, so it is OC squared equals to KC squared. KC is 2, therefore KC squared is 2 squared, that is 4, plus OK squared. OK is 2, therefore OK squared is 2 squared, that is 4, plus KC squared. KC is 6, therefore KC squared is 6 squared, that is 36. So total we found out that OC squared equals to 4 plus 36, that is 40. So OC squared equals to 40. Here we took out of this equation. We found out that OC equals to the square root of 40. We substitute 40 by 4 times 10. We took 4 out of the root, so the square root of 4 is 2. Inside the root we left only with 10. So in total we found out that OC equals to 2 times square root of 10 units in its term. In this right angle OKC, this is the angle alpha, this is the right angle, and therefore this part means angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. 90 degrees plus 90 degrees is equals to 180 degrees. It is the sum of the angles in any triangle. Likewise, this right lower triangle KYC, this is angle alpha. This is the right angle, therefore this part means angle must be equal to 180 degrees in the side, according to the sum that said that the sum of the angles in any triangle is equal to 180 degrees. So the next step we prove that the big right triangle OKC can go is similar to this right small triangle KYC according to angle side rule. So when those triangles are similar to each other. First of all, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself is a common side that belongs to both triangles. It's a common angle that belongs to both triangles. In addition, those two angles are both right angles, and therefore they are equal to each other in this other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So in total, we found out that all the triangles of this right big triangle OKC are correspondingly equal to all the triangles of this right lower triangle KYC. Therefore, those two triangles can run to each other according to angle M and angle similar to. Repeat again, in total, we found out that the big triangle OKC is similar, this is the sign of similar, to the small triangle KYC according to angle similar to. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side OK of the big right triangle OKC, or side KY of the small right triangle KYC, is equal to side OC of the big right triangle OKC, or side KC of the small right triangle YKC. This again from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side OK of the big triangle OKC over side KY of the small triangle KYC is equals to side OC of the big triangle OKC over side K is equals to side OC of the big triangle OKC over side KC of the small triangle YKC. OK is 2 over KY is X, and this is equals to OC, that is 2 times root of 10 over KC, that is 2 times root of 10 minus X minus 2. So in total we found out that 2 over X equals to 2 times root of 10 over 2 times root of 10 minus X minus 2. Here we have 2 on both sides of the equation, so 2 will get cancelled. After we cancel 2, of course multiply this equation, and finally found out that 2 times root of 10 minus X minus 2 equals to the square root of 10 times X, or X times root of 10. Here we added X to this equation, so in this side of the equation we left only 2 times root of 10 minus 2. Here we added X, so it is equals to X. This side of the equation we have X times root of 2 plus X. Here we took 2 as a common factor out of those two expressions, so inside the brackets we left only with root of 2 minus 1. Likewise, we took X out of this common factor from those two expressions, so inside the brackets we left with root of 2 plus 1. So in total we should find out that 2 times root of 10 minus 1 equals to X times root of 10 plus 1. Here we divided this equation by square root of 10 plus 1. And finally found out that X equals to the square root of 10 minus 1 over square root of 10 plus 1. We multiplied this to the side of the equation by square root of 10 minus 1, and then we divided by square root of 10 minus 1. Again, we multiplied this expression by square root of 10 minus 1, then we divided it by square root of 10 minus 1. So in total we found out that X equals to the square root of 10 minus 1 times the square root of 10 minus 1. That is actually, here we have 2. Here we have 2. So it is 2 times square root of 10 minus 1 squared. And it equals to square root of 10 plus 1 times square root of 10 minus 1. According to this algebraic identity, that states that a plus b times a minus b equals to a squared minus b squared. We get that square root of 10 plus 1 times square root of 10 minus 1 equals to the square root of 10 squared, that is 10, minus square root of 1 squared, that is minus 1. So in total this expression equals to the square root of 10 minus 1, that is 9. So X equals to 2 times square root of 10 minus 1 squared over 10 minus 1, that is 9. So in total X equals to 2 times square root of 10 minus 1 squared over 9. Repeat again, in total we found out that X equals to 2 times square root of 10 minus 1 squared over 9. Our task is to find out the area of this green circle. Actually we know that the area of any circle equals to pi times the radius of the circle squared. So the area of this green circle must be equal to pi times the radius of this circle squared. The radius of this circle is x, therefore the area of this green circle equals to in total to pi x squared. The area of the green small circle equals to pi x squared. But we only found out that x equals to 2 times square root of 10 minus 1 squared over 9. So we substitute x by 2 times square root of 10 minus 1 over 9 squared, because it is x squared. Here 2 over 9 squared is 2 squared, that is 4 over 9 squared, that is 81. So we left inside the square only with square root of 10 minus 1. And in total we should find out that the area of the green circle equals to 4 pi over 81. We open the brackets here, square root of 10 minus 1 squared equals to the square root of 10 squared, that is 10, plus 1 squared, plus 1 squared, that is 1, minus 2 times square root of 10 minus 1, that is 2 times square root of 10, all squared. So it is 4 pi over 81, and 10 plus 1 is 11. So here we have 11 minus 2 times square root of 10 squared. So in total the area of the green circle equals to 4 pi over 81. Here we open the brackets here. 11 minus 2 times square root of 10 squared equals to 11 squared, that is 121, plus 2 times square root of 10 squared is 2 squared, that is 4, times square root of 10 squared, that is 10. 4 times 10 is 40. So in total this expression equals to 40. Minus 2 times 11, that is minus 22. Minus 22 times 2 is minus 44, times square root of 10. 121 plus 40 is 161. So we have here 161 minus 44 times square root of 10 units in itself. Okay, in total, the value of this expression, that is to say 4 pi over 81 times 161 minus 44 times square root of 10 is equals to 274.7 square meters in size. Repeat again, we actually found out that the area of this again small semicircle equals to 274.7 square meters in size. So we finish to repeat on the first question. In the next step we repeat on the solution of the second question for both methods. In the second question, our task is to find out they have this quarter circle A or B. So in the drawing we have quarter circle A or B. This is a right angle, this is also a right angle. QB equals to 1 unit in length. We also know that OQ equals to PQ. Again, our task is to find out the area of this quarter circle A or B. So in the first step we define the radius of this quarter circle. This is to say AO and OB is x. And so OB equals to x, and therefore OQ equals to OB minus QB. So OQ equals to OB, this is x, minus QB, this is 1. So in total OQ equals to x minus 1 unit in length. But OQ equals to PQ according to what is given, answered in the question. So OQ equals to x minus 1, therefore PQ must be also equal to x minus 1 unit in length. In the next step, we completed the quarter circle to a circle, and then we extended the radius BO by side line until it touches the circle. We defined the extended radius BO with this circle, and the point of the extended, the touching point of the extended BO with this circle. This point is point N. Likewise, we extended PQ by side line until it touches the circle. And we find the touching point of the extended PQ with this circle. This point is point M. Actually, if we divide this circle to those two semicircles, and NB is the axis of symmetry between those two semicircles. That is to say, point NB is the axis of symmetry. Those two semicircles they are identical, but the lower semicircle is the mirror image of the upper semicircle. Likewise, QM is the mirror image of PQ. Why? Because of the fact that if we flip the upper semicircle on the other side, point P and M will merge with each other. Therefore, because of the fact that point P and M will merge, it means that PQ equals to QM. Like if you look in the mirror, you see your mirror image. That is to say, you see yourself exactly as the same size that you are in reality, but in the opposite direction. So QM is the mirror image of PQ, so for PQ equals to QM. But PQ is x minus 1, therefore QM must be also equal to x minus 1 in its length. So in the next step, we implemented rule 65 in our drawing. So repeat quickly rule 65. According to rule 65, if code AB intersects with code CD 8.0, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule 65 in our drawing. One point in our drawing, this is code NB, it intersects with code PM at point Q. Again, it's code NB intersects with code PM at point Q. Therefore, according to rule 65, the following equation is to NQ times QB equals to PQ times QM. Again, NQ times QB equals to PQ times QM. And again, according to rule 65, the following equation is to, first of all, because of the fact that code NB intersects with code PM at point Q, we can implement rule 65. According to rule 65, NQ times QB equals to PQ times QM. NQ in total equals to x plus x minus 1, that is 2x minus 1, times QB is 1, PQ is x minus 1, and QM is also x minus 1. So in total, we found out that 2x minus 1 times 1 equals to x minus 1 times x minus 1. X minus 1 is x minus 1 squared equals to 2x minus 1. So 2x minus 1 equals to x minus 1 squared. X minus 1 squared equals to x squared, plus 1 squared is 1, plus 2 times x times 1, that is minus 2x. So 2x minus 1 equals to x squared plus 1 minus 2x. So here we substituted 2x for this equation. And I found out that here we have 2x minus 2x is 0, and it equals to x squared. Minus 2x minus 2x is minus 4x plus 2. So total, we found out that 0 equals to x squared minus 4x plus 2. In the end, total, we found out that x squared minus 4x plus 2 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is as follows. X squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus 4 to b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared minus 4x plus 2 equals to 0, the variable that we are looking for is x, and x is the radius of this quarter circle. The coefficient a equals to 1, the coefficient b equals to 4, and the coefficient c equals to 2. So we have all the data that is needed in order to find out the radius of the quarter circle, that is x. We just have to put the data inside this general formula for x, and this way we find out the value of the values of x, because x might have two solutions. So we did it, and we found out that x equals to minus b. B is minus 4, therefore minus b is minus 4, this is plus 4, plus minus square root of b squared. B is minus 4, so b squared is minus 4 squared, that is 16. Minus 4 times a times c. A is 1, so minus 4 times 1 is minus 4 times c. C is 2, so minus 4 times 2 is minus 8. So in total inside the root we have 16 minus 8, this is 8. So in total we found out that x equals to 4 plus minus, square root of 8 over 2. We substitute 8 by 4 times 2, so in total we found out that x equals to 4 plus minus, square root of 4 times 2 over 2. We took 4 out of the root, the square root of 4 is 2, inside the root we left only with 2. So in total we found out that x equals to 4 plus minus 2 times square root of 2 over 2. Repeat again, in total we should find out that x equals to 2 plus minus square root of 2. So here we have two solutions that are possible for x. The first solution for x is as follows. X equals to 2 minus square root of 2. 2 minus square root of 2 is 0.59. And this is line segment OQ. This is equals to x minus 1. OQ equals to x minus 1. So OQ is a length, and the length must be a positive number. And the value of OQ is x minus 1. So OQ is a length and must be a positive number. But OQ is x minus 1, so x minus 1 must be a positive number. What is a positive number? It is a number that is greater than 0. So in total, we have found out that x minus 1 must be greater than 0. We added 1 to this inequality and finally found out that x must be greater than 1. So x must be greater than 1. If x must be greater than 1, x can never be equal to 0.59, that is less than 1. So we cancel the first solution for x, and we took into account only the second solution for x. The second solution for x is as follows. X equals to 2 plus square root of 2 units in its length. Our test is to find out the area of this quarter circle A or B. The area of any quarter circle equals to the area of the circle over 4. The area of the circle is pi x squared because x is the radius. So the area of the quarter circle must be equal to pi x squared over 4. So it is pi over 4 and x is 2 plus square root of 2 squared. So in total we found out that the area of the quarter circle must be equal to pi over 4 times 2 plus square root of 2 squared. This expression in total equals to 9.55 squared in size. So we found out that the area of this quarter circle A or B is equals to 9.155 squared in size. So we finish to repeat on the first method. Next step, repeat on the second solution of the second method. The second method, we define the radius of this quarter circle. We define the radius of this quarter circle as x. So AO equals to OB equals to x. The above the radius of the quarter circle is equals to x according to our definition. OQ equals to OB minus QB. That is to say, OQ equals to OB, this is x, minus QB, this is 1. So in total, OQ equals to x minus 1. But OQ equals to QP, and OQ equals to x minus 1, therefore QP or PQ must be also equal to x minus 1 within its length. In the next step, we join points O and P together by straight line. By joining points O and P, we created green triangle POQ. So in the next step, we implemented the Pythagoras theorem on this green right triangle POQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So in this right triangle POQ, PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. And again, right triangle OPQ, according to the Pythagoras theorem, PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. PO is x, therefore PO squared is x squared, plus PQ squared. PQ is x minus 1, therefore PQ squared is x minus 1 squared, plus OQ squared. OQ is also x minus 1, so OQ squared must be equal to x minus 1 in its length. X minus 1, OQ squared must be equal to x minus 1 squared. So in total, we found out that x squared equals to x minus 1 squared plus x minus 1 squared, that is 2x minus 1 squared. So in total, we found out that x squared equals to 2 times x minus 1 squared. So x squared equals to 2 times x minus 1 squared. X minus 1 squared equals to x squared plus 1 squared, that is 1, minus 2 times x times 1, that is minus 2x. So x squared equals to, open the brackets here, 2 times x squared is 2x squared, plus 2 times 1 is 2, plus 2 times minus 2x is minus 4x. So total we found out that x squared equals to 2x squared plus 2 minus 4x. Here we subtract x squared from this equation, so on this side of the equation we left with nothing, that is to say 0. While on the other side of the equation we have 2x squared plus minus x squared is x squared minus 4x plus 2. So total we found out that x squared minus 4x plus 2 equals to 0. This is the same quadratic equation that we had in the first method, and only found out that the solution for this quadratic equation is x equals to the square root of 2 plus 2. Our task is to find out the area of the quarter circle AOB. So the area of this quarter circle AOB must be equal to pi x squared over 2 because of the fact that the area of this quarter circle is x. So the area of this quarter circle must be equal to pi x squared over 4. But x is square root of 2 plus 2, so we substitute x by square root of 2 plus 2 squared. So in total, the area of this quarter circle equals to pi over 4 times square root of 2 plus 2 squared. The value of this expression in total is equals to 9.155 square inches in size. So in both methods we found out actually that the area of this quarter circle equals to 9.155 square inches in size. Okay, thank you very much.